Okay, so in this video, I'm gonna go through how to make an OR gate with NPN transistors. Um, I'll also be recapping on the logic gate, the OR gate itself, and then I will actually go through not a common misconception, but a misconception about an OR gate. I'm not saying that any of you guys have had this misconception. It's just that I would like to address it. Okay, so first the recap, right? Um, so I'm gonna recap the behavior of an OR gate by using the help of a truth table. So if you would like a more in-depth explanation on the OR gate itself, or if you want to find out more about other logic gates, just go and watch the previous video I have about OR gates, which goes more in depth about it and stuff. So the condition for the output of the OR gate to be true or 1 is that if either A or B is 1. So and transcribing the information onto this truth table, it will look like this. It will look like this, yeah. So if both are 0, then it'll be 0. But if either one is 1, as you can see here, then the output will be 1. So that's pretty much it. Yeah. That is um, the recap of the OR gate. So now let's actually move on to the how to make an OR gate with the NPN transistor. So here, yep, that is how you do it. Let me just bring this up. Okay, so this is how you configure it. You got this is your power, this is your ground. You got your two transistors, NPN transistors, and there's a resistor. So to explain how this configuration acts as an OR gate, right? I will go through each case for the truth table and then just visually show what's happening. So this is our output, right? The way to get the output is to have the current flow from here, which is the power source, all the way here, right? So this is what we want to happen. And the thing is that these two transistors are actually stopping this from happening. So for example, right, let's say the circuit has to be completed this way. It can't because this transistor opens the circuit at this bit here. So actually it doesn't go through here. And the same case for here. It cannot complete through here because this is open here lah. Okay. So I mean that's pretty much the explanation for A and B lah. I mean for this case here. When A and B is 0, there is no current flowing through here. So now these two transistors act like they act like they open the circuit basically. So now this would be the current cannot flow through like this, and the current cannot flow through like this as well. Cannot flow through like this as well. Yeah. So that is for this first case. The next case where okay, A, there is no current, and B, there is actually current. So current flows through here. So when current flows through here, it completes the circuit here. And what that does is, right, it actually allows current to flow through here and here. It actually allows current to flow through here and here. So when one is open, when this BGT is closed, right, the circuit can actually complete, and then the output is 1. The output is 1, as you can see here. Okay, next, if this has current and this has no current, same story. Now this is closed, so current can actually flow through here, and it grounds here, right, and it also goes through here. So now the output X is also 1. And then the last case where both are on. So now both act as closed. yeah, both close the circuit. So current flows through here, which flows through here, and then like it does the same here as well. It does the same. So now the output is still 1. And that is the explanation. That is how this configuration works. Very simply. So you may be wondering, right, what is the point of this part at all? Because technically, right, if I just remove this and then have this output, it still works. Like in like let's say this case, right, A is 0, B is 1. If current does flow through here, right, it closes this bit, right, and it actually still works. So what's the point of that bottom bit? Okay, this is for protection. Okay, in the case where let's say okay you're using an OR gate, right, and then your output there's an LED and it grounds lah. Like let's say there's an LED and it grounds. This is okay. Then this bit is actually useless. But let's say this doesn't exist. Okay, now this has no output lah. And in some cases, right, in a practical setting, this is true. This will happen. Then um you it would be better, right, for when this is closed to have a grounding area actually. Um okay, now yeah, now I'm starting to doubt it myself. Let me see if this is true. I mean, yeah, it's actually, yeah, that's true. Also, right, actually the reason that I just said like a few seconds ago might not be the main reason. Because technically, even then, right, you can just remove it. Then you could argue that the current wouldn't go anywhere, but that's false. The current will go somewhere. If you have no load and you didn't have this ground, not ground protection, if you didn't have this like extra bit here, let's say like this is on, right, and this is not, then current would flow through like this, and it there is a slight possibility, right, if there's some like kind of grounding error here or parasitic capacitance or whatever, that it may flow back and damage some things. Okay, just just go with the flow. Just go with the flow and have this here. Yeah. So that's the configuration and the explanation on how it works for the OR gate with 2 NPN transistors. Now let's move on to some common misconceptions. Okay, not common, just a misconception. So you may ask, okay, why do I even need a transistor at all? What if I just have this? Okay, what if I just like connect the two wires together, right, and then have the output like that? Technically it works, right? And to that I'll say maybe it might work. If you like, if you follow a truth table, like if both are 0, then your output is 0 because there's no current here, there's no current here. Hold on. There's no current here, there's no current here. So technically there's no current here. Yeah. That's all. That works. That works. Then technically, if there's no current here, but there's current here, it will technically flow through, right? Yeah. You're right. And if there's current in both, technically it will flow through. Yeah, you're right. So why can't I do this? You can't do this because it's dangerous. Okay. Let's say there's this case, right, where there's no current at A and there's current at B. You may get the expected output, right? But there's a chance the current flows back through A, and then damage like previous components. That's mainly the that's mainly the reason why you should not make an OR gate like this. Yeah. Um, and as this smart ass here has just said, use diodes, which is what I was about to get to. So yes, in the case, the main case why you don't use this is because current can flow back. So just use diodes. Okay, I'll just use diodes then. Ooh, so now it's appropriate, right? Wrong. Okay, so if you say everything is fine and dandy, you may be right, but there's just so many drawbacks. Okay, there are more drawbacks to this than this. Okay. So let's see. It works, by the way. I'm not gonna re-explain why it works. You can just use the same explanation from this one. So if you have like this case, there's no current here and there's current here, it will go through and then it won't go back here. But here's the thing: this component takes up 0.7 volts. It eats up 0.7 volts of your main uh of your power here, around 0.7 volts. Most diodes take up 0.7 volts. Um, so this is not, if you're making a very low precision circuit, which you, in the case or where we are all doing our coursework, right? Technically, you can do this, but it's very frowned upon. If you do this circuit right, and you write it in your report, it is not gonna look very nice. It's like I don't know. It's just a bad thing. Yeah, I can't come up with an analogy for this. But just don't do this, mainly because these diodes eat up your voltage. And in this case, right, there's like very little eatage. Yeah, so you don't want to do this. Okay, and then that's pretty much it. But I'm also gonna talk about the pros and cons of using uh NPN transistor logic gates and the actual IC chip logic gates, which I which I mentioned in the previous video, which was about the NAND and AND gates. So you may ask you may ask yourself, right, or you ask me or someone. Oh wait, before I do that, let's just cancel this out. Yeah. Okay. You may ask you okay, why do I even need to care about this? Why do I even need to know about this? Can't I just use the logic IC chip? And my reply to you is that that's a very valid argument. However, the IC chips, right, have their own cons, and the NPN transistor logic gates has their own pros and cons as well. To the point where, right, it is totally okay if you use logic gates with transistors or with IC chips, and it totally depends on your use case. That means, right, neither outweighs the other in terms of usability or in efficiency or whatever. So basically, right, both are viable options. The pros for the IC chip, right, is that it is very properly done. It looks cool. Uh, there's like one, two, three, four, five. There's 8 or 6 logic gates in one chip, which is quite a good deal. The cons are that for okay, the cons are that if you don't treat the IC chip properly, then it's not going to treat you properly. When you're going to use an IC chip, right, you have to ensure that your inputs are digital signals. So what you're gonna have to do is you're gonna have to do some signal processing. So you process your input before actually putting it into the IC chip. And if you do this wrongly, your output, right, may be false. It may not even work. And also in your IC chip inputs, right, there's some grounding issue that everyone is facing right now for some reason, and I don't know why. um, and if you don't like ground your inputs properly, that means like if your input is like a floating value, it's not going to work as well. So those are the pros and cons for IC chips. The pros and cons for the transistor is, the pros is like you're not going to have this finicky issue. You don't have to even do signal processing. That means like even if your input is floating, right, or not properly, 5 volts or close to 5 volts, if that is your logic one, it's still going to work well. um what are the other pros? It gives you more to write about in your report. If you play your cards right, this is if you play your cards right, this is at least 2 or 3 pages in your report already, which to me it's nothing, but to y'all it's everything because your report only 15 pages. My report is 70 pages. I don't even care. My report is going to be 100 pages. So um that those are the pros. The cons is like there are so many lah. The cons are it takes up space. The IC chip has 4 logic gates in one, but this one is going to take up a little bit more or space that the IC chip will take, and it's only one chip. It's only one gate. Um, yeah, so it neither method outweighs the other, and it is really dependent on your use case. For my use case, I actually use IC chips and um, NPN transistors for my logic gates. I use both. Yeah. So it is very up to you. And the reason why you need to know this is because you need to know that there is another option. And if right now you are facing an issue where your logic gate IC is like acting up or whatever, and and for like most of the people I help, right, they're only using one gate and then they're already encountering issues. Just use this. Just use this. Don't even waste your time. Time is so precious. So that's why you need to know this, and you need to know this now. Okay. So yeah, that's it.